Okay. But it's better to attend the class at the same time, and we can communicate whenever you have questions. Okay. Today's topic is about continuity. Before I do that, I needed to talk about the meaning of approaching to some number at some point in the XY plane or in the space. Okay. So first of all, let's consider the two-dimensional case. So we have an x-axis, y-axis in the plane. It's a fixed. And here's a point A and B, okay? And this is a point that's called P, okay, with coordinate. And this is another point, Q, has coordinates X and Y, right? So what's the meaning of Q approaches P? What's the meaning for that? Yeah, by the, when we say Q approaches P, okay, that means it's getting close to P, right? So Q which approaches P, okay? Means Q is getting close to the point P. Now, how to say that in mathematics, right? So we know that the distance between P and the Q is going to be given by this formula, okay? So when we say Q approaches P, means the distance between P and Q is getting smaller and smaller, okay? So this is equivalent to saying this approaches 0, okay? A number approaches 0, okay? Now, this is square root, so same as you can move the square root out, remove this approaches 0, okay? So that's the meaning. So this also implies X approaches A and the B approaches B, Y approaches B, okay? So this implies X approaches A, otherwise the square and the plus addition term will be not, right? And Y approaches B, okay, at the same time. The mass is equivalent. If X approaches A, Y approaches B, then the corresponding point, here's a point, okay? Here's how do you understand this? This is A, that's a B, right? And that is X, that is Y. So if X approaches A, Y approaches B, or the corresponding point Q approaches P, okay? So we understand this, okay? Now, maybe we, there's a very precise definition about the continuity of the function using delta epsilon language. It's very abstract. What I want to say is, roughly speaking, is when we say have a function as a limit, right? First of all, let's talk about limit here. When we say a function is continuous at a point, okay, if the limit of the function as Q approaches P is the value of the function at that point. So first of all, I have to talk about the limit, okay? So what's the mean limit, okay? What does it mean a limit? Here's the definition of the limit, okay? When we say the limit of x, y approaches A and B, f of x, y equals L if, okay, if the value of the function approaches L as x, y approaches A and B, okay? Okay, so this is the mean, okay, it's a number. F of x, y is a number, okay? This number approaches another fixed number. Now, then we say this function has a limit. That's the first part. So we have to define the limit, okay? Now, there's a very precise definition for the limit, okay? That means for any given And this is this is pretty, it's easy to understand this part. But if you want epsilon language, epsilon delta language to define it, that means for any small epsilon, okay, there is a number delta, okay, as this depends on the function, it depends on epsilon at least, such that, okay, the value of the function, the difference between the two numbers is very small than the given number. Whenever the distance between those 2 points is smaller than that. Okay, so this is if this is a Q, that's a P, that is actually the distance between P and the Q. Okay, the same. So sometimes we just use the coordinates to describe the point. Sometimes we just simply write a point. Okay. Right. So this is a abstract definition. It's really hard to use this to prove the limit exists. Okay. Okay. Because I remember that when I was teaching Math 165 there, right, and there was the definition about the limit of a function as x approaches a, and I have to prove that the limit of the function equals some number, and not every student will fully understand. Okay, if you understand that part, then you can understand this part. But we probably still have to use this to prove the limit of function exists. Okay, now to prove the limit of function does not exist, it will be much easier. Okay, so take the so how to disapprove a function as a limit doesn't exist. Okay, well, this is as a necessary condition is, if the function approaches, okay, if the function approaches, if the limit exists and equals L, that implies, okay, this implies that this is a point, and P was A and B, okay? This is any path Q, that is X and Y. So that implies f of X approaches L for the point, okay, approaches A and B along any path, okay, any path to go to the point P, okay? So I didn't mention the path at the very beginning in the definition. When I say this is this approach, that means from all the direction approaches that point, okay? So so that means so this is slightly different here, just along a path, okay? If along all the directions, when the point Q approaches P, f of Q approaches L, then of course along this particular path, any particular path that works, okay? And so that means if this is not guaranteed, then the limit doesn't exist, okay? Suppose here's a situation. Suppose this is point P and Q, right? And you have one path. This is another path. Okay. So if this is a path C1, this path C2. Okay. Now if the function approaches L1 as X approaches and B along C1, but f of X approaches L2 as X, Y approaches AB along C2. okay? And L1 is not equal to L2, then the limit doesn't exist, okay? Because it says that the limit exists if when then along any path that approach the same number, right? Then this one does not exist, okay? Does not exist, okay? So this is a very useful idea method to prove that the limit does not exist, okay? So let's use, let's take a look at some examples, okay? It's much harder to prove a limit exists than prove the limit does not exist, okay? So take a look at the following function, okay? F of x, y, which is going to be x squared minus y squared, x squared over plus y squared, okay? We want to check whether this one has a limit, okay? Now, I said that the limit doesn't exist, okay? Well, first we can check that along different paths, okay? Along different paths. This is an axis, y-axis, right? Okay. Along the x-axis, this is going to, along the x-axis, that's my thing, right? I want to change along the x-axis, okay? So x and y is going to be y0, okay, right? And then f of x, y is going to be f of x0. So when I plug 0 for y, then I get x squared minus 0 squared, x squared plus 0 squared, which is x squared over x squared, and that's just always 1. So along this line, the function has constant value. So that means it approaches 1, of course. Now let's try another one along the y-axis, okay? Along the y-axis, and the x value is going to be 0, right? Yeah, the x value is going to be 0. So f of xy, now when you do the homework, or show the work in a quiz, you have to write this, okay? So you have to clearly tell me which two passes you consider. Okay, so get 0 squared, y squared, and 0 squared plus y squared, and this time is always -1. And so they're different. These two numbers are different. So the function, so your conclusion is f of x does not approach any fixed number as x and y approach the origin. Okay, so what you conclude that does not approach, okay, a fixed number that's x and y approaches the origin, okay? Because when x and y, when the point approaches the origin, this approaches in any direction, okay? So there are lots of freedom, infinite many passes approaches that, or even strict line, okay? So imagine the function along some passes approaches 1, sometimes approaches negative, and then some places approaches maybe infinity, I don't know. Yeah, it's not necessary to know all the pictures. We just needed to know, along two different passes, and the function, the value of the function approaches two different values of function approaches to different values. And then the limit doesn't exist. Okay, so it's easy to prove the limit does not exist. Okay. Okay. So let's try another problem. Okay. Let's try another problem. So this time f of x, y, is going to be x times y, x squared plus y squared. All right. So this function, what is the domain of this function first? Okay, the domain of this function is going to be all the x and y, and x and y cannot be 0, right? So x squared plus y squared is not going to be 0. Otherwise, you get 0 over 0. So x squared plus y squared is not going to be 0. So that means this cannot be the origin. So this will be the whole plane and delete the origin, okay? So that's a notation. So the function is defined in the whole plane away from the origin, okay? Yeah, so, but you still can talk about the limit as x as a point. This is a point P, here's a point Q, okay? And you still can talk about the limit as Q approaches P, okay? But I guess this one does not have a limit, okay? Because applying different approaches, I think you're going to get different values, okay? I'm going to choose x-axis, but next pass is not going to be the y-axis, okay? So first of all, let's look at C1, the x-axis, okay? The x-axis, okay? All right, so now we have along this axis, right? So x and y is going to be x0, okay? So f of x and y is going to be when y is 0, here's x squared plus 0 squared, and that's clearly 0. It's identical, it's 0. So of course it approaches 0, right? As x and y approaches the origin, okay? Yeah. And the C2, now if you choose the y-axis, you end up with the same result. It still approaches, the value of the function approaches 0 around the y-axis. So it will be inconclusive. You cannot say the limit exists because you haven't checked all the passes, right, toward the origin. When I say Q approaches P along any passes, any path, okay? And the value of the function, you know, roughly speaking, yeah, f of Q, I just use a Q approaches L as Q approaches, right? P, that's a question mark, right? We have to verify this. Then Q approaches P along any passes. I have to send the value of the function at the Q, at the point Q approaches the same number. So we have to check that. So if you use a y-axis, yes, you still get 0, right? Along the y-axis, you know. Let's try this, okay? So in this case, f of x and y, I think x is 0, y is a variable, and that is going to be 0y, 0 square y square. This is going to be identical 0. This approaches 0 as x and y approaches the origin, okay? So inconclusive at this point. I cannot say the limit of the function is 0, okay? So I choose consider another path. Another path is the following, okay? I choose this one, middle, any other line. It's not necessarily the x-axis, y-axis, okay? Any other line, okay? So that line could be I choose an arbitrary point. Yeah, this is this is A and B. Okay, along this path. Okay, so along this line. Okay, this is a line we call C3, right? Okay, so X and Y can be expressed in the form A and T, B and T. Okay, but this is not going to be x-axis or y-axis. Okay, yeah. So this approaches 0 if and only if t approaches 0. It's the same, you know. Okay. All right, so let's take a look at this. So that'll be AT x, right? And BT, that's y. That's AT squared, right? And BT squared. Then let's simplify. So it's going to be ABT squared. A squared, you have t squared, right? Plus b squared t squared, so I can take a t squared out. So what I got is just a squared plus b squared. So that is a limit this approach here. So so you can say that f of x approaches a squared plus b squared as xy approaches 0, 0 along C3, okay? But clearly, this is not a constant, not a fixed number, okay? This is not a fixed number. Different values A and B get different, right? So this is not a fixed number, okay? So along different lines approaching the origin, the value of the function approaches a number depends on the direction of the line. Okay, it's not a fixed number. Therefore, this limit of this function does not exist. Because when it exists, you have to show that they all approach the same number. All right. Now, I have another one. The next one is the limit exists. Okay, here's the fx. I get x squared. I can, x squared. I can put the y squared here. No, it doesn't matter. Okay, y squared, x squared plus y squared. And why this one has a limit? As x as a point approaches 0 origin. This just because the degree of the numerator as a polynomial. The degree of the numerator as a polynomial is degree 4. The degree of the denominator is just only 2. 4 is larger than 2. So the numerator approaches 0 faster than the denominator. Okay. So this whole quotient approaches 0. Okay. And why the other one is not? See, this one, x times y over x squared plus y squared. The degree of x times y is going to be 2. Okay. The degree of the polynomial. Okay. So let me put a note here. Degree of the polynomial, that's 2. Degree of x squared plus y squared equals 2. So they are approaching 0 at the same rate. Same rate does not mean exactly, the same way. Maybe one is faster, one is slow, a little bit slow. So they end up with the quotient, okay, approaches the different numbers, okay. But here, okay, here the degree of the numerator is going to be 4. So the degree of the denominator is going to be 2. Okay, so that means as x and y approaches, that means as x and y approaches 0, 0, okay, origin, so x squared per y squared approaches 0 faster than, that's not very precise, but you can see that faster than x squared plus y squared. So the quotient will approach 0. Okay. They are at a different rate, right? Completely. So the question is, how can I show this is true? Okay. How can I show this is true? Okay, I know the result already. The limit is going to be 0. How can I do that? The best way to solve this problem is going to be using some inequalities. Okay, so here's the important inequality. Okay, let me get the inequality. We have a yeah. So a plus b squared equals a squared plus b squared plus 2ab, right? Okay. Yeah, I'm trying to. So then if you have the difference, okay. So that means this has never been negative, right? I use the second one. So that means 2ab is less than or equal to a squared plus b squared, always true. Okay, you can use an absolute value. Okay, ab not necessarily positive, then you put absolute value, it's the same. Okay. All right, so this is an important inequality where we have used it over and over again. So a and b less than half of a squared plus b squared. Okay, you should know this from. Okay. All right. So now we come to the function. Okay, we look at x squared times y squared, x squared plus y squared. I'm trying to use the following. Okay, x squared plus y squared is x times y here. Okay, then I have x squared times f times y. Now above the inequality tells me. Okay, above the inequality tells me this is going to be the less, both of them has an inequality, right? So they are satisfying. I can keep that, right? They're satisfying the first one, half of x squared plus y squared. Second one, half of x squared plus y squared. Divided by x squared plus y squared. So now what do you get? This cancels out, right? So you get 4 x squared plus y squared. This is very interesting inequality. Then you conclude that. That's why I said it's the more difficult to prove it exists. So as x and y approaches 0, 0, okay? Equivalent to saying that x squared plus y squared approaches 0, right? I just say IE. And then because the absolute value is less than this, so by this inequality, okay, by this inequality, x squared plus y squared, okay, approaches 0. This is by the encoding. Because this is bounded by another number, that number approaches 0. Of course, it's called squeeze theorem. Okay, so therefore we conclude that this this proves that the limit as xy approaches 0, 0, x squared y squared, x squared plus y squared is going to be 0. Okay. But you have to say, you have to give some argument. That's not easy to do. Now, how about, if I modify a little bit, okay? If I modify a little bit, I get x squared just y. How can I do that? Okay, find the limit as x. I believe this limit is still going to be 0. Why? Because the degree of x squared y is going to be 3. And the degree of x squared plus y squared is going to be 2. Degree of a polynomial in 2 variables. So the numerator still approaches 0 faster than the denominator. So the quotient approaches 0 as the xy approaches 0 and 0. All right, how can I do that? Well, I still need the encoding. Okay, I pursue the value x squared y and x squared plus y squared. I just need the x, right, and the x times y, right? Okay, so the second part, I keep the x, absolute x. The second part is half of x squared plus y squared. Okay, and then cancel that. So I get pretty simple. That is okay. Okay. But that one actually, this actually is going to be square root of that's okay. Yeah, using polar coordinates is fine. Use a transformation, it's fine. So that is going to be x squared plus y squared. Okay. So this is equal. Why this equal is true? Because first of all, I have this. If you let the y to be 0, you get absolute x. Okay, and this is going to be that. Okay. So now it's clear that as x and y approaches 0, 0, okay, then x squared plus y squared approaches 0, okay, then x squared y, this approaches 0, okay, because it's bounded by numbers getting smaller and smaller. Okay, so my conclusion is right. Now we have a student asking whether we can use the polar coordinates to prove that. That's probably fine. So we can. Here's a point, right? Polar coordinates. That's a good idea, actually. It's a great idea. Polar coordinates. The relationship between polar coordinates. Okay, x equals r cosine theta, y equals r sine theta. Okay, so x squared plus y squared equals r squared. So x and y approaches 0, 0 if and only if, right? X squared plus y squared approaches 0 if and only if I approaches 0. So make it simple, just one variable approaches 0. Okay, it's independent of theta. Okay, that's a good idea. So you can make a transformation. Okay, it's called substitution, but it's two-dimensional substitution. So let's take a look at this function. Okay, this function is going to be x squared y, right? X squared plus y squared. Now, if you use this substitution, what you get here is x is r square cosine square theta, and y is going to be r sine theta. Okay, and here just r squared. Okay, right? It's probably much easier. So what you get here is The numerator is r cubed, denominator r squared. So it's r cosine square theta sine theta. Okay, this can change the sign, right? But then it's clear that when r approaches 0, this part is bounded, right? When r approaches 0, this approaches 0 as r approaches 0. Okay, that'd be a good idea, right? It's independent of theta. The reason is r cosine square theta sine theta is less than or equal to r. So if r approaches 0, the term inside of absolute value approaches 0. Okay, okay, note that. Okay, so therefore, you can simply write this is the limit r approaches 0, and after you simplify it, it's the same. Okay, let me okay, you can simply write like this. And this is r cosine square theta sine theta, and that's just 0. You ignore the theta. Theta is arbitrary value. Okay, that's a good idea. Much easier maybe. Yeah, especially when you see x squared plus y squared. Now that works, okay, for this type of problems, but not always works for other type of problem. If I modify a little bit, then you may have a problem. Okay, let's look at the one problem from the book exercise. Okay, I'm trying to find yeah, so 14. Okay, so the limit so again x cubed minus y cubed x squared plus x times y plus y squared. First of all, when I look at this, I find out this limit should be 0. The question is how do you prove it? Right? If you use the polar coordinates, I don't think we'll make it easier. Maybe it's making it easier, maybe not. Okay, we can try. Okay, that works because it's a homogeneous function, so probably it's okay. I'm trying to do different ways. So let x to be r cosine theta, y to be r sine theta. Okay, so now this is called substitution. Okay, so x cubed y cubed x squared plus xy plus y squared is going to be r cubed cosine cubed theta minus r cubed sine theta. Okay, and this will be r squared cosine square theta, and twice, so r squared cosine theta sine theta plus r squared sine square theta. Okay. All right, so now the numerator is r cubed, and you have this, right? The denominator is r squared. You have lots of this, okay? So after you simplify it, you only have one r here, and then you have something depends on sine theta cosine theta, okay? You have to say that the denominator never be 0, okay? So this is a small issue here, you cannot say, yeah, for the denominator, yeah, the denominator never be 0. Okay, x squared plus x times y squared. So it's a little bit complicated. But this one should be bounded. It's independent of theta. Otherwise, I know r approaches 0, but how do you know this is no impact about your limit, right? This would be a challenging problem. Okay, so you have to say this is not going to be an issue. Okay, so you have to say that. No, it's not easy to do this. Okay, how do I do that? Okay, cosine square theta plus sine square theta plus cosine theta. You still have to use a lot of inequality here. It's 1 plus cosine theta sine theta, right? And then you can also write like a sine 2 theta. But I know sine 2 theta's value is between negative and positive, so it's greater than or equal to 1 minus 1/2. So that's the smallest value. It's never be negative. You see, it's not easy to check that, right? So this whole expression okay, is going to be less than or equal to, the numerator is 1 plus 1. Do you agree? Okay, because absolute cosine theta is 1 less than or equal to 1. Absolute of sine cosine sine theta is also less than or equal to 1. The denominator, you have to get a lower bound, it's 1/2. So actually it's 4. This whole expression, the value, is never greater than 4. So that shows that it's going to be greater than 0 as r approaches 0. Because the second part, we're not getting smaller and smaller. The second part, we're not getting larger and larger. So the product is still getting smaller and smaller. Okay. So this is not easy, right? If you use polar coordinates here to prove. But still, we successfully prove that. So this is my conclusion is a limit. Okay, x squared, now x cubed, y cubed is going to be 0. Okay, but for this particular problem, there's a quick way to do. Okay, when you see x cubed minus y cubed, this is just x times y. Right? You should know that you factor it. Okay, so when you factor it's x minus y, x squared plus xy plus y squared. Yeah, this is a required. Yeah, this is required in pre-calculus. So we should know this this formula. So then cancel it out. So after simplifying, just x minus y. Okay. And it's guaranteed, obviously, this is, if we put a absolute value here, this will be absolute value, this absolute. Now, why this difference approaches 0 when x squared plus y squared approaches 0? Well, this is less than or equal to, right? And clearly, this approaches 0 as x squared plus y squared approaches 0. Okay, why it's clear? The reason is x squared plus y squared, right? That is going to be, x squared plus y squared approaches. That means that implies x squared approaches 0 and y squared approaches 0. So that implies x approaches 0, y approaches 0. Of course, then have the absolute value approaches 0. Okay. So that's what the sum approaches 0. I think it's not easy to prove the functions the limit exists. Right? Be very careful when you. But you look at the numerator and denominator both. If they are polynomials, you look at the degree. If they have the same degree, the limit usually does not exist. If they have a different degree, yeah, the degree of the numerator is larger than the degree of the denominator, and maybe the limit exists. All right. All right. So now about continuity. After we talk about limit, then we can say continuity. Okay. we say that a function, so this is a picture. This is a domain D. Here's a point inside, okay? And the function is defined on this domain. We say that F is defined, F is continuous. That's the definition. F is continuous. Continuous at the point in the B if two things. First of all, the limit exists. Not only exists, should be equal to the value of the function. Okay, that's two things. So if the limit doesn't exist, then you cannot say the function is continuous. Okay. So if the value of the function doesn't exist, then you cannot say the function is continuous at that point. Okay. That's my experience. Okay. Let me write this. Then we said the function is continuous on domain if it's continuous at every point inside the domain. Okay. Now, very important fact is if okay, here's a fact. Okay. If f of x is expressed by elementary functions, okay, in x and y, then f is always continuous on its domain. Okay, this is very similar to the function with one variable. Okay, what does that mean? Okay, here example. If you look at the f of x, x squared plus x times, right? This is a polynomial. It's an elementary function because you can write that clearly. Okay, elementary function use a sine, cosine, or whatever. Okay, square root and products, polynomials. Okay, so the domain of this function is the whole plane. Okay. Okay. Now this function is the whole plane. Right. So what is? Then it's limit. Then you can find the limit. Just plug the number in. Okay. So let's say approaches 1 and 3, right? So f of x. All you have to do is you just look at the value. Okay. So that's going to be 1 square plus 1 times 2 plus 2 square. So it's 1 plus 2 plus 4, which is going to be 7. Okay. So we can use because the function must be continuous at that point. So the limit is just the value of the function. Okay, it's easy to find the limit if you know the function is continuous. All right. My next question is, okay, let's consider this function. Right. So is it continuous? My answer is, where is this continuous? Right? My answer is it continuous at the origin? But the function is not defined at the origin, so of course it's not continuous. Okay, it's called discontinuous. So how to answer this question more precisely? So first of all, let's figure out the domain. So domain of this function are those points such that the denominator is not going to be 0. So this is a whole R2 by removing the origin. Okay, this means minus. Okay, delete the origin. All right. So the circle, this is deleted. Everywhere else, it's fine. Okay, so the domain is a whole plane without the origin. According to above theorem, okay, for any A and B not at the origin, okay, the limit of x and y approaches A and B is just equal to the value of the function. It's very simple. So just a squared plus b squared, a squared minus b squared. All right, so we find it. Okay. And the function is continuous at that point. Okay. F is, in other words, f is continuous at this point. At any point away from the origin. But the function is not defined, so you don't need to talk about discontinuity. Okay, because the point is not even on the domain. So there's nothing you can talk about. Okay. Is a function continuous at the origin? You cannot say anything because the first condition is the function must be defined at that point. It's not defined, right? But I can make a function defined. I can make it defined. Okay, if x squared plus y squared is aware, it's not going to be 0, right? When it's 0, assign any value. I just say here, if x squared plus y squared is 0, that means that it's origin. Okay, I can define this, right? Yeah, sometimes you can say x and y is not going to be the origin because x and y is going to be the origin. Okay, so this is define f. Yeah, the domain of f is a whole plane. Let's define everywhere. Okay, how can I tell where the function is continuous? I think from above argument, first, f is continuous at any point, okay, and the b which is not going to be the origin. Okay, clear. But how about the origin? Because it's already defined, so I can talk about continuity. How about the origin? Well, we see that we have to find the limit, right? F is continuous at the origin if and only if the limit exists, right? And should be equal to the value of the function. But the value of the function, I already know that's 0. So so you have to prove that limit is not exists, but also equal to 0. And we already did that, the limit doesn't exist. Okay, however, the limit does not exist. Okay, I think we already did this at the very beginning. See the first example we discussed. Yeah. See the first example above. Okay. All right, let's take a look at another picture. Okay. Okay, now let's go to the book. I'm going to look at some expressions. Okay, determine the set of points at which the function is continuous. That's cool. So we can look at some examples. And let's look at example 32, okay? E to the x plus e to the y, e to the x times y minus 1. All right, so first of all, we have to make sure it's a domain, we have to find the domain. Okay, essentially, this is a problem just for us to find the domain because this is a function defined by elementary function. Okay, by elementary function. So what is the domain? The domain of the function are those points such that e to the xy minus 1 minus it's not going to be 0. Okay, otherwise it's not defined. Okay, so let's take a look at this equation. This is equivalent to say x times y is going to be 0, right? Because that's the only possible case. So x times y is 0. What does that mean? That means either x is 0 or y is 0. But if x is 0, you get the y-axis. If y is 0, you get the x-axis. Okay? So now I have a pretty good idea. The domain consists of 4 regions away from the axis, y-axis. So the domain df is going to be the plane with the x-axis and the y-axis deleted. Okay. So it consists of 4 pieces. Okay. And the function is an elementary function. So we conclude that f is continuous on its domain. So if you find the domain, then you get the set at which the function is defined. Okay. Yeah, let's take a look at number 34. So given a function, all right, so take a look at this. First of all, let's find the domain. All right, the domain is the domain, let's use a G, right, called DG, okay, domain G. It's going to be the set of those points such that the 1 plus x minus y should be greater than 0. Because natural log is only defined for positive number, right? So if it's 0, then it's not. It's not defined. If it's negative, it's not defined. So 1 plus x minus y, let's understand this in code. Okay, this is the same as x minus y greater than negative 1. Now, it is better to use level curves to understand this picture. Okay, let's look at x minus y equals k. X minus y equals k. Let's do this as our opposite side. Okay, I'm going to move y minus x less than 1. Okay, so I use because I want to talk about lines. So y should be part. Okay. So y minus x equals k. Here y minus x less than 1, right? So when k equals 0, I get this strict line. Okay, that's k equals 0. And k equals 1, this line. K equals 2, this line. right? So x minus y less than 1. So it's very clear for you. That's going to be the region of that, right? Right, using the level curves, it's much easier to understand the region. So the function is defined over that region. Okay, so that is a domain. So the function clearly, by the fact we were told, this function is continuous on its domain. Okay, so G is continuous on its domain, and described by this picture. Okay. Yeah, because this is an elementary function. It's not like a piecewise defined function. Elementary function is one piece. Okay, using x, y, natural log exponential function. Okay. Problem number 30. Problem number 37 is yeah, I'm going to modify this problem, okay? Problem number 37, it's not 37, I'm going to use this one. X squared y cubed, x squared plus y squared. Okay, in the book, it's also put 2x here. So that is going to be 0 if x and y, we can determine what is the value of k. Yeah, so here's if x and y is not equal to 0, 0. Right, so we want to find the value of k so that this becomes a continuous function everywhere. Is it possible? Okay, so questions, is it possible to find k such that f is continuous at the origin? Because it's continuous away from origin, no problem. Why? Because it's away from the origin, the function is a quotient, is defined by elementary function. So it's continuous, no problem. The only trouble is to determine the value. So as long as the function is continuous, the limit exists, then the value of k can be determined. So actually k should be equal to, okay, should be equal to this limit if it exists. I'm going to put a 2 here, make it just a little bit strange, okay? So that's a 2x squared plus 1. Okay. I believe that the limit exists. Not only exists, it must be 0. How? Okay, so look at that. The degree of x squared y cubed is going to be 3. But the degree of the 2x squared plus y squared is still going to be 0, is going to be 2. So 3 is larger than 2. So the numerator approaches 0 faster than the denominator. So the limit exists. Limit should be 0. Okay. So let's take a look at this. I think it's a limit issue. So now it's clear to us we have to prove the limit exists and none exists, it's going to be 0. Okay, how can I do that? Right? I record the important formula. Okay? this is yeah. So this is going to be less than or equal to half of x squared plus y squared. We keep using this, okay? So x squared y cubed, 2x squared plus y squared is going to be less than, okay? It's going to be equal to, first of all, right? So we get absolute x and then x absolute y, right? This is square. And here 2x squared plus y squared. So I can use above encoding. So it's going to be absolute y half of x squared plus y squared and the square, right? Because absolute. Now, we cannot cancel it immediately. Why? We cannot cancel x squared plus y squared. But I can make the, I can remove the 2 here because makes the denominator smaller than you make this larger. Then you're okay. Okay, then you can cancel those 2. So my answer is, okay, I can also replace the y by x squared plus y squared, square root, okay? So this is going to be less than or equal to an x squared plus y squared and it's 1/2. Okay, so then after combine them, okay, so this is a very a good estimate. And clearly this approaches 0 as x squared plus y squared approaches 0, okay? As x and y approaches 0, 0, it's the same. So that, okay, the absolute value of this is bounded by this another term, right? And this term clearly approaches 0 when the point approaches origin. So my conclusion is, here's x squared y cubed is going to be 0. Okay. Yeah, remember there's a lot of trick here. The trick here is that when is absolute of x is less than or equal to x squared plus y squared and it's 1/2, okay? Of course, the first inequality is going to be, okay? And then the y is also is less than or equal to, okay? Another important identity is going to be, that's a trivial identity, right? Like a 2x squared plus y squared is less than or equal to x squared plus y squared. The reason is you make the denominator smaller than the quotient is large. So those are the points, yeah, you have to get familiar with. It's called algebra, okay? So that if you feel difficult for this part, and that means your algebra is a little bit weak, but it's okay, you practice, and this is the time to improve your algebra skill too, okay? It's not, maybe, when you took algebra before, you did not do well, but does not mean you cannot teach algebra in high school, for example. Why? Because after finish the calculus course, your math, yeah, it's improved, right? So you go back, it's no problem. So here's the general rule. A student, A+ student in math, graduate from high school only, cannot teach high school, okay? Cannot teach high school, even he can tutor students, but cannot teach. And but if you always get a B in math, but you get a bachelor degree in mathematics, you are qualified to teach high school math. Okay? So it sounds like a bit strange, but that's true. Okay? Because so many courses you take, your view on mathematics is different, and you also, you keep a practice, and you that's why you already, if you take a test on algebra in high school algebra, you already get A+ by that time. But you have more knowledge about mathematics. Okay. All right. So